Okay, let's unpack this. Have you ever stepped outside on a really cold morning or maybe into just sweltering summer heat and felt your body immediately like kick into high gear,
Hmm.
just trying to keep you comfortable? It feels like more than just a feeling, doesn't it? It's this invisible, complex dance happening inside you and around you
Hmm.
constantly.
Yeah.
Today, we're diving deep into the surprisingly complex science of heat and cold.
And it's a really critical deep dive too, because understanding this fundamental balance, it isn't just about feeling good.
Right.
It's profoundly important for your health, your safety, even how well you perform tasks.
Mm.
This deep dive, it's going to pull back the curtain on those unseen thermal forces,
Hmm.
the very real dangers that come with temperature extremes, and importantly, the clever science-backed ways we measure and manage them.
Yeah, manage them in our daily lives. That's right. So, our mission for you today is really to equip you with some insights into how your body manages its temperature balance, this delicate thing. What happens when that balance, when it goes wrong, and crucially, what practical steps you can actually take based on, the science. Get ready to feel much more informed about your own thermal world.
Definitely.
So, let's kick things off with the absolute core idea.
Yeah,
Our bodies, they're dynamic living systems. We're not just sort of passively taking the weather, are we?
not at all.
We're constantly balancing the heat we make inside with the heat we swap with the environment. It's like this finely tuned machine, always adjusting.
Exactly. And we can actually sum up this constant adjustment with, a neat little equation,
Yeah.
MCR0.
Okay.
Now, that looks a bit technical, but it's basically a blueprint for how your body handles temperature. Let's break it down.
Yeah, please.
Okay, so first M, that stands for metabolism. This is the internal heat your body generates just by, existing. All those cellular processes, they produce heat,
Right, like a little furnace inside.
exactly like a furnace. Even sitting still, you're generating heat. And when you exercise, that M factor, it shoots way up. You feel warmer almost instantly because your cells are working much harder.
Okay, so that's the internal heat production. Got it.
I've got it. Next up, C. That's convection. This is about heat transfer through movement of air, or even liquid right over your skin.
Ah, like a breeze cooling you down.
Precisely. A fan feels cool because it strips away that warm layer of air next to your skin, letting more heat escape. But, flip side, step into a blast of hot air, and convection can actually dump heat into your body.
Makes sense.
Then we have R for radiation. This is about heat exchange between your body and the surfaces around you. It's not just sunshine, though. That's a big one.
Okay.
It's also why standing near a cold window in winter makes you feel chilly,
Oh,
even
that
if the room air isn't that cold. Your body radiates heat to the window. And you absorb radiant heat, too, like from hot pavement in the summer.
Right. I've definitely felt that heat coming off the asphalt. That's radiation.
That's it. And finally, E for evaporation. This is your body's, ultimate cooling mechanism, mainly sweating.
The big ones.
The big one, yeah. It's your most effective way to shed heat. But, and this is crucial, it really struggles in high humidity.
Ah, okay. That explained why sticky heat feels so much worse.
Exactly. 30 degrees Celsius in a humid place feels way more oppressive than 30 degrees in a dry desert. Because if the air is already full of moisture, your sweat just can't evaporate properly.
Ah,
The E and R equation basically stalls.
okay. This is where it gets really interesting thinking about daily life because obviously, what's one of our main ways we manage this whole balance?
Hmm.
Clothing. I mean, think about it. Clothes act as insulation. They slow down that heat transfer, whether it's keeping heat in when it's cold or sometimes even keeping intense heat out.
Right, they trap air.
Yeah, they trap air close to your body, and air is a surprisingly good insulator. And there's actually a standard unit for this, isn't there? The Clo unit.
That's right, the Clo unit. One Clo is roughly what typical business attire provides in terms of insulation.
So when you're putting on layers, you're basically doing your own little bit of thermal engineering, managing those M, C, R, and E factors.
You absolutely are. And understanding these four mechanisms, metabolism, convection, radiation, evaporation, plus the role of clothing, it's just fundamental to grasping how we stay comfortable and, more importantly, how we avoid getting sick in different climates. It's this constant, invisible negotiation.
So we've established this delicate balance, but, what happens when the heat just gets to be too much, when the environment overwhelms our body's ability to cope? Let's turn to the hazards of hot environments now.
Yeah, when the body can't shed heat effectively, we start seeing a range of pretty serious heat illnesses.
Uh-huh.
The most severe, the one that's potentially fatal, is heat stroke.
Okay.
This is basically a catastrophic failure of the body's temperature control system. The body just gives up trying to cool down. A really scary sign is often a lack of sweating. The skin is hot, dry, red.
Wow, no sweating. That's counterintuitive.
It is, but it shows the system has failed. Core body temperature shoots up dangerously fast, often over 40 Celsius. That's 104 Fahrenheit. Immediate aggressive medical help is absolutely critical, life or death.
That sounds terrifying. A total system shutdown. So for something maybe a bit less severe, like heat exhaustion, how can you tell the difference between that and just being really worn out from the heat?
That's a really good question because they can feel similar at first. Heat exhaustion happens because you've lost too much water and salt through heavy sweating. But here's the key. The body is still trying to cool itself.
Okay.
So symptoms are things like fatigue, nausea, headache, maybe dizziness, and often the skin might feel cool and clammy, or they'll still be sweating profusely. That sweating is a big difference from heat stroke.
The sweating is still happening with exhaustion.
Usually, yes. The critical sign to watch for is if symptoms worsen quickly, or if the person starts getting confused or disoriented. That's a major red flag. Time to cool down and get help.
Got it.
Then you've also got heat cramps. These are painful muscle spasms, usually in the legs or abdomen,
Right.
from losing too much salt through sweat, especially if you're not used to the heat.
Right.
And lastly, there's heat rash or prickly heat. Just skin irritation from blocked sweat glands. Uncomfortable little red bumps, but usually not dangerous.
And it's not just internal illness, is it? Intense heat can also cause direct burns to the skin.
Absolutely. And we classify those by depth. First degree are superficial, like a sunburn redness, maybe mild pain. They heal pretty quickly.
Okay.
Second degree burns go deeper. You get blistering, significant pain. These are more serious.
Right.
And then third degree burns are the worst. They destroy the full thickness of the skin. It might look white or leathery or charred. These are medical emergencies, often needing skin grafts and specialized care.
Wow. Okay, so how do we, predict or assess the risk of these things happening, especially, say, for people working outside?
Well, that's where heat stress indices come in. A really important one is the Wet Bulb Globe Temperature Index, or WBGT.
WBGT. Heard of it.
Yeah. It's clever because it's not just air temperature. It combines air temp, humidity, using that wet bulb idea we talked about, radiant heat from the sun or hot objects, married with a special black globe thermometer, and sometimes air movement. It gives a much more realistic picture of the total heat stress your body is experiencing.
So it's like a real field temperature, but for overall heat stress?
Kind of, yeah.
Yeah.
But specifically geared towards physiological strain.
Yeah.
Organizations like the ACGIH, the American Conference of Governmental Industrial Hygienists, they actually provide threshold limit values, TLVs,
Okay.
based on the WBGT reading and how hard someone is working. These TLVs recommend safe exposure times and work schedules to prevent heat illness before it starts. It's about proactive safety.
Okay, so that makes a lot of sense. We measure the risk using things like WBGT.
Huh.
Then what does this mean for us practically? How do we actually control the heat or mitigate the dangers?
Good question. We usually think about controls for heat in a few main categories. First is source control. If you can, insulate the hot thing itself, like lagging around a hot pipe in a factory. Reduce the heat getting out in the first place.
Makes sense. Stop it at the source.
Exactly. Second, environmental modification. This is things like using powerful ventilation to suck hot air out and bring fresh air in, obviously air conditioning where possible, or even just putting up reflective shields to block radiant heat from reaching people.
Right, changing the space itself.
Then there's activity adjustment. This is crucial. Reducing how hard people are physically working, making sure they take frequent breaks in cool areas, and setting up formal work rest cycles to limit how long anyone is exposed to the heat.
So managing the work itself.
Mm-hmm. And finally, if you can't control the source or environment enough, there's protective equipment. This can range from simple things like hats to specialized gear like water-cooled vests, air-fed suits, or even shiny reflective suits for really intense radiant heat, like firefighters wear, or workers near furnaces.
Wow, quite a range of options there. It really shows how layered the approach has to be. Okay, so that covers the heat side pretty thoroughly, but of course, heat is only half the story. Let's flip the script and talk about the cold.
Absolutely, because just like heat, cold environments pose their own unique set of dangers. Our bodies struggle when that balance tips too far towards heat loss.
Yeah. So what are the main cold-related illnesses we need to be aware of?
Well, the one most people think of is probably frostbite. This happens when your actual tissue temperature drops to freezing or below. Ice crystals literally form inside your cells, causing damage. It typically hits the extremities first: fingers, toes, nose, ears.
Ouchie. I think I might have had mild frost nip on my ears once skiing. Even that was pretty unpleasant warming up.
It can be very painful, yeah. Then there's something called trench foot. Now this is interesting because it doesn't necessarily require freezing temperatures. It's caused by prolonged exposure to cold, damp conditions, even if it's above freezing.
Ah, so wet and cold, not just freezing cold.
Exactly. Wet feet lose heat much faster. It leads to numbness, tingling, swelling, blisters, and can cause lasting nerve and tissue damage in the feet. Historically, a big problem for soldiers in trenches, hence the name.
Makes sense. And the really big one for overall body temperature.
That would be hypothermia. It was a dangerous drop in the body's core temperature, generally below 35 degrees Celsius or 95 Fahrenheit. It's insidious because it affects brain function.
How so?
Well, early signs are uncontrolled shivering, maybe some confusion. But as it gets worse, the shivering might actually stop. Speech becomes slurred, coordination fails, drowsiness sets in, leading to loss of consciousness. It's a true medical emergency and can be fatal if not treated promptly by warming the person carefully.
Scary stuff. And just like with heat stress indices, there are ways to measure cold stress too, right? I always hear about wind chill on the weather forecast.
Exactly. The Wind Chill Temperature Index, or WCT, is the most common one. And it's a really useful concept. It basically tries to quantify how cold it actually feels on your exposed skin when you factor in the wind.
Right, because wind makes a huge difference.
A massive difference. Wind strips away that thin layer of warm air right next to your skin, the boundary layer your body tries to maintain. So the faster the wind, the faster you lose heat. The WCT gives you an equivalent temperature of what the air would have to be, with no wind, to have the same cooling effect. So -5 degrees might feel okay if it's calm.
Yeah, manageable.
But add a strong wind, and the wind chill could make it feel like -15 or colder, meaning the risk of frostbite goes up dramatically. It really highlights the danger isn't just the thermometer reading.
Okay, so knowing the risks, frostbite, trench foot, hypothermia, and understanding things like wind chill, what are the key controls for cold? How do we protect ourselves?
Again, we can think in categories.
Mhm.
First, environmental modification. If possible, use heaters, especially localized ones like radiant heaters, to warm up work areas. Setting up windscreens or barriers is also huge for cutting down that wind chill factor.
Block the wind. Makes sense.
Second, activity adjustment. Pretty straightforward. Minimize how long people have to be out in the severe cold. Provide warm, easily accessible shelters or break rooms for people to regularly warm up. Schedule work to avoid the coldest parts of the day if you can.
Right. Limit the exposure time.
And third, and probably most critical for personal protection, is protective clothing. Layering is absolutely the name of the game here,
Why layers specifically?
because trapped air is the best insulator. Multiple thin layers trap more air than one thick layer, and you can adjust them if you get too warm from exertion. You also need good protection for the extremities: insulated gloves, warm socks, hats. You lose a lot of heat through your head.
Always wear a hat, my mom used to say.
Good advice. And crucially, the outer layer needs to be wind resistant to combat that wind chill. But ideally, it should also be breathable, allowing sweat vapor to escape. Getting wet from sweat makes you much colder much faster, so windproof but breathable.
Okay, that's a really comprehensive look at both sides, heat and cold. We've talked about the effects, the risks, the controls. But how do scientists and, safety professionals actually get the numbers? How do they measure these conditions out in the real world?
The measurement instruments. Yeah, to get the data for things like the WPGT or just general assessment, we rely on a few key tools. They're often simpler than you might think.
Like what?
Well, for basic air temperature, it's just a standard thermometer. We often call it a dry bulb thermometer to distinguish it.
Okay.
For humidity, we need to know how much moisture is in the air. This is usually found by comparing the dry bulb reading with a wet bulb thermometer reading basically a thermometer with a wet wick around the bulb. The difference tells you about evaporation and thus humidity, often done with a device called a psychrometer.
Right, wet bulb for humidity.
Yep. Then for that mean radiant temperature, the effect of hot or cold surfaces, we use a special thermometer inside a flat black globe. It absorbs radiation, much like your skin does, giving a measure of that radiant heat load.
A black globe thermometer. Got it.
And finally, for airspeed, which we need for convection and wind chill calculations, we use an anemometer. Could be a spinning cup type or a hot wire type.
So thermometer, psychrometer, black globe, Anemometer.
Those are the main ones.
Yep.
And what's really neat, I think, is how these fairly straightforward instruments, when used together correctly, provide the detailed data we need to apply all the science we've been talking about to understand the risks and actually protect people. It really grounds it all in practical measurement.
It does. This whole deep dive has really highlighted the incredible complexity, but also the elegance of how our bodies manage everything. This constant battle or maybe dance with the environment. From that internal metabolic furnace to the cooling power of evaporation, it all comes back to keeping that heat balance equation in zero, as close to zero as possible. It's just happening silently all the time.
It really is. And if we connect this to the bigger picture, this knowledge isn't just interesting facts. It's genuinely powerful for your own well-being.
How so?
Well, it informs your choices, what you decide to wear, how hard you push yourself when it's really hot or cold, and crucially, recognizing those early warning signs of trouble, whether it's heat exhaustion setting in or the first tingles of frostbite. It lets you shift from just experiencing the weather to actively, intelligently managing your interaction with it. It's about informed action.
Informed action. I like that. It empowers you to safeguard yourself. Absolutely. So the next time you step outside, whether it's into that, crisp autumn morning air or really humid summer afternoon, just take a second. Consider those invisible forces we talked about, that constant, intricate dance of heat and cold happening within you and all around you. How might this deeper understanding change the way you interact with your environment? Maybe how you dress or plan your activities. Keep that curiosity going. Stay balanced out there.